Good afternoon, everyone. I hope I am going to keep all of you awake after a nice lunch. All of you enjoyed your lunch or not? Yes. Perfect. So today I am going to talk about CO2 capture, utilization, and sequestration. So suppose there is a reaction where A plus B plus C goes to D. You need to have all A plus B plus C together. If you have one of it in larger amount, the entire reaction is not going to happen. So the capture, utilization, and sequestration, all three are equally important. Okay, so with that, let me start with this particular slide over here. So when we say capture, utilization, sequestration is shown over here. So capture could be from direct capture from air. I know industries are very attracted to this concept of direct capture from air. Then there is something called point source capture, where typically the concentration of CO2. Okay, fine. So I'm going to see this light is going on my eyes actually if I'm going to close. That's fine. Oh, okay, that's no problem. So we will talk about all this. And then once you have captured the CO2, why do you need to capture the CO2? In this particular case over here, what is the concentration of CO2 in the air? Right now it's roughly 400 ppm. Let's say even if it is 500 ppm, one of the challenge which you are going to face is capturing one molecule of CO2 which is surrounded by 10,000 other molecules, which is mostly nitrogen and oxygen. CO2 is a very large molecule. It has high potential energy, very low kinetic energy, so it's relatively easy to capture CO2. But the problem is that since one molecule of CO2 is surrounded by 10,000 molecules of nitrogen, and nitrogen being a very small molecule, it basically constantly bombards the CO2 molecule, does not allow it to rest. So typically what happens if you are going to capture one molecule from 10,000 molecules surrounded by something else, you need a material which has to chemically bind to this CO2. Means this material, if you talk about a magnet, you need a very strong magnet to bind one of those molecules which is hidden somewhere in 10,000 molecules. So you always would need a chemical which is going to bind this particular CO2 molecule, and that's how it would basically separate it out. You cannot do it by physical solvent. We'll talk about it later. But before we go into that, let's give you a number which is shown over here. 2.8 billion tons of CO2 is being produced by India every year. Now, if we are talking about a chemical which is going to capture one molecule of CO2 from 10,000 molecules of nitrogen, the best molecule possible to capture this CO2 would be in the ratio 1:2, 1:10. It means you need 10 such molecules which is going to capture one CO2 molecule. There is nothing better than that. The best molecule today, you would at least need, so for example, 10 weight% capacity is what typically we say. You cannot have anything better than that today for capturing 500 ppm or 400 ppm CO2. Okay, so basically that means you are going to need 28 billion tons of that particular molecule. Now this is per year, increasing at a rate of 5% to 6% every year. So by 2030, we will be around 6 billion tons of CO2 per year. Even if you want to be, by 2030, you want to be closer to this number, our target is 1 billion ton. Let's say we are going to capture only 1 billion tons of CO2. You see, we need 10 billion tons of that particular material. Okay? And that material is not going to come from thin air. It has to come from the same sources which we know all about. We have to dig something from under the earth, and we'll have to purify it, repurify it. We do 100 kind of processes, and all of these processes will be done by what? Will be done by fossil fuel. So it's not that the CO2 which you are capturing over here is the only number which you have to look at. The material, and I'm talking about the material which will go inside. I have not even talked about the steel which is being consumed here and the plastics which are being consumed over here, and the cement which is being consumed over here. For next 40 years, neither we are going to have green steel, neither we are going to have green cement. neither we are going to have any other green processes. Everything will be done through the same fossil fuel. The recent estimate is that the green cement will, at max, will start coming from 2045. So we are stuck to this cement and the steel and all. So look into this unit over here. Many people would say that we should have a prototype which will capture CO2 from air. This unit, as soon as you put on Earth, it has already contributed 10 years worth of CO2. It means this unit will become net CO2 zero after 10 years. Okay? So this 10 years sitting outside, we're getting all the kind of weather, whether this will run for 10 years, I don't know. I know one data though. Many of us would have bought our air purifiers at home. It has become very popular. It is now in our cars, it is now at our home. Every room pretty much have air purifiers. Just go and look at the data, whether your air purifier ran for more than 5 years. Most of the air purifiers went bad in 2 years, some went up to 3-4 years. More than 5 years, none of your air purifier would work. It means you have generated all kind of CO2 just by getting that material, and then you are throwing it out even before 10 years. It means you are not getting net zero CO2. In fact, you are generating CO2. So if you really want to capture CO2 direct from air, you better plant a tree. This is not the right approach. I'm going to always talk about the material efficiency over here. Obviously, in terms of money, let me tell you, the CO2 capture from this unit is $500 per ton. $500 per ton is the current cost of CO2 capture from this kind of unit. And if it can be improved further, it would go slightly lower. So for example, $400 per ton. So this is the story of CO2 capture from direct air. Okay. Now let's come to the problem is that why do you need to capture CO2 from direct air? If tomorrow all the cars are going to be EV, you don't need to capture CO2 from direct air. The CO2 in the air is coming from this. So why we should go here and capture our CO2? Rather, let's capture CO2 from here. And what are these? These are cement industry, these are steel industry, these are coal-fired power plant or any other fossil fuel power plant. The concentration of CO2 over here are going to be 10% to 30% CO2. Other gases would be oxygen and nitrogen. So going by the same analogy, now you are going to capture one CO2 molecule out of maximum 10 other molecules, or probably 5 other molecules. So now it's much easier for you to capture or catch hold of this CO2 molecule because you don't have to differentiate between many people. You know that this is the CO2, the other 5s are not the CO2. It was very difficult to do when you had one CO2 molecule and 10,000 other molecules. In this particular case, now I have one CO2 molecule and now I have to go and catch that CO2 molecule, and the other molecules are only 4 or 5, so it's much easier for me to do that. So here you don't need a chemical which will interact with or which will react with CO2. You can go with a chemical which is going to interact with CO2. There are two kinds of forces when we talk about interact with CO2. We talk about van der Waals interaction, and the chemical bonding is chemical bonding. So what I'm trying to say, if you have higher concentration of CO2, you don't really need to go for a chemical which is going to react with CO2. Because when A plus B reacts to produce C, unfortunately, it's not only C which gets produced. AC will also form, BC will also form, and C square will also form, or CC will also form. So when you are going to regenerate this material, because I was telling you there are 10 tons of material which will be required to capture tons of CO2. So you will have to regenerate this material because you are producing it by producing huge amount of CO2. So even 0.1% of material is lost during this recycle of regeneration. Within 5 years, entire material will be gone and you will have to produce new material. Exactly same amount of material within 5 years. So basically it's important for you to understand, if you can avoid a chemical reaction between this solvent and the CO2, it's always better. Go for a physical solvent where there is no chemical reaction and regeneration is much easier. So you are not going to lose any material over there. So the advantage over here is obviously in terms of cost, in terms of CO2 emission, because the amount of material which I am going to need over here will be not 10 times of this, but only twice of this. Okay, so that's the advantage. I am not producing as much CO2 over there. And also you can see in terms of cost, it's only $30 to $50 per ton. So if you are going to capture CO2 from point source, it's going to be much more inexpensive and you will be able to capture the CO2. Now the next question is, how much total it is going to cost if you have to capture this CO2? It's 25% of total energy penalty. So for example, a power plant which is producing 500 megawatt of electricity, just for capturing the CO2, I'm not even talking about utilization and sequestration, just for capturing the CO2, 25% of the total production electricity will be consumed. It means a 500 megawatt plant will become a 375 megawatt power plant because the remaining 125 megawatt will be consumed in capturing the CO2. Whatever we have done so far is that we have dug all our fossil fuel from under the earth, we burn it, and then utilize the energy, and the CO2 we just release to the atmosphere. We are not bothered to make it sustainable. So if you are going to make it sustainable, you have to capture the CO2 and then put it back under the earth if possible. So the cost which we are paying so far is only half of the cost. Remaining half we are not paying, and this is why we are not used to it. So it's important for us to understand that it will cost money if we are going to make this process sustainable. There is no other way out. Fine, let's move further. So this capture is done. Once you have captured, what you are going to do? Capture the CO2, what is your option? Either you utilize it or you sequester it. Okay, again, industries like to utilize it. Always the term will come, we want to monetize this problem. This is a big problem, and I am pretty sure you cannot monetize it. Let me tell you what is the problem in monetizing this problem. See, in short term to medium term, you cannot monetize it. 50 years to 100 years down the line, probably it might be possible, but not today. The reason I am going to tell you, what you are going to get out of it, you have got pure CO2, let's say, after you have captured it. The pure CO2 is what all the research which today people talk about is CO2 utilization, that we will mix it with how you will utilize CO2 and what is there to utilize. Let me break it down. There is C and there is O2. C, which we don't want because we say that fossil fuel, coal and all is burning and going to produce CO2, so I don't want to burn C. And O2 is oxygen, what you will utilize there. You can get it from the air. Okay? If you are going to utilize CO2, you will have to mix hydrogen in one form or the other. It's as simple as that. So you should look at it from a point of view of transporting hydrogen, because today you don't know how to transport hydrogen in a proper manner. This is why, because it's a gaseous molecule. So this is why you might mix it with CO2 and produce a liquid fuel, which will be easier for you to transport. But in long run, I don't know whether it is going to make a lot of sense, because what you are going to do, you have burned carbon plus oxygen and produced CO2. Now you are saying that I will use this CO2, mix some hydrogen into it, and then convert and make it fuel. So the problem is, if you already have hydrogen, why would you mix it with CO2? Hydrogen is a much more valuable product. If you are utilizing CO2 by any other mean than using hydrogen, it makes sense. But if you already have hydrogen, which is a much more valuable product, why you would mix with CO2 to utilize it? So that is another problem. And also the other problem is this. In next slide, I will tell you. This is one unit, which is the largest unit which is being built right now. 160,000 tons of CO2 will be converted to methanol. This unit is being produced here, and it's being using the CO2 from a cement plant and CO2 and hydrogen from a coking furnace plant. You know, I'll give you a data. This is 2 minutes worth of CO2 emission. So much of investment, and how many of these units you are going to put? 100 units? 1,000 units? How many of these units you are going to put around the world? So the point I'm trying to make is that whatever you do, utilization is going to only be suitable for maximum 10% of CO2 which you are going to produce. You cannot get away from sequestration. So the investment for sequestration has to be done, and it has to be done now, not tomorrow, because it's for next 20, 30 years, the CO2 is going to go to the atmosphere. And if you are not using any green way to capture this CO2 and sequester this CO2, it's going to go up and up every other day. Okay, so the point I was trying to make is that utilization is necessary, but however best utilization technology you have, it cannot utilize more than 10% of the CO2 which is being emitted today. Remaining 90% of the CO2 you have to worry about what you are going to do. And the only method for you, is to sequester it. There is no other way out. Sequestration you cannot avoid. There are multiple ways of sequestering CO2, and if someone thinks that there are not enough resources where CO2 could be sequestered in India or around the world, that is not true. There are significantly large amount of CO2 sequestration options, and it can sequester CO2 for next 100 years. And by that time, if you really know how to do this circular economy where CO2 is being converted into oil and you feed back into the same system, that's going to be so the assumption that we can fix this CO2 emission problem and still make it economically attractive, at best it is naive. I don't believe that we can really make it economically attractive. You cannot. Right now, 3.5 rupees per unit is the cost of electricity production if you are using coal from India. And if you are using imported coal, it's around 4.5 rupees per unit. With this cost of around $30 to $50 per ton, it comes out to be 1 rupees per unit for CO2 capture and another 1 rupees per unit for transportation and sequestration. So at max, a 3.5 rupees per unit electricity cost is going to be 6 rupees per unit if you are going to make it sustainable by capturing and sequestering the CO2. And by doing this, you are not emitting any CO2 to atmosphere. And what is the cost? The cost is that instead of paying 3 rupees, 4 rupees, you are paying 6 rupees. That's it, nothing more than that. Technology do exist, investment has to be done for doing something like that. Now the second point I am trying to make, I'll show you this particular unit. Looks very nice. You see world largest solar plant in Abu Dhabi, 2 megawatt capacity roughly at INR 2 per unit. You will say why we should not go to renewable energy. This is the solar energy, the most greener form of energy. I will show you this, and then I will show you this. You see where all your elements are coming from, and in what conditions these people are. Before I show you this, and I also show you a small data again. You know, similarly, similar to this problem, there has been another problem which we have faced in Tuticorin. 1994, a unit was built by, at that time it was called Sterlite Copper Smelting. This company, I don't want to go in detail, but produced huge amount of copper. And for whom? 70% of that copper was exported. So you polluted your country for someone else. That is what they are doing now. Now let me tell you that some numbers. So as I was telling you, CO2 emission by coal-fired power plant is around 500 gram per unit. So 1 unit of electricity if you are producing, you are producing 500 grams of carbon dioxide. And let me show you some numbers for solar panel. The CO2 emission in fabrication of solar panel, I have done a good amount of literature search. There are variation in numbers, but the solar panel production will produce around 50 gram per unit to 115 gram per unit of CO2. It means if you are, and this is distributed over 20 years of lifespan for a solar panel. So what I am trying to say that the day you are putting this solar panel, if you do the calculation for 20 years of lifespan, you have generated 75 gram of CO2 per unit of electricity which you are producing from this solar panel. And this solar panel is only producing for 6 hours a day. It means, because that is when the sunshine is there, it means you have to install 4 times this capacity. Multiply this with 4 times, and then you have to look into the storage which you will have to do for the 18-hour, the battery storage or whatever storage you have. You add the CO2 emission from the production of batteries, it comes out to be 360 gram per unit. Does it look too different? Does not look too different. The so-called green energy is already producing 360 gram of CO2 per unit. So, and I don't want to do the cost analysis. The cost analysis of CO2 capture, sequestration or utilization is actually much better than a green field. And I have not even told you this number that the material which is going into this is right now controlled by a couple of countries I don't want to name, but one particular country produces 75% of your solar panel. Another particular country gives 50% of the material which is required for which goes into this solar panel. So you really want to be bound to those countries. This is something which you'll have to worry about. So what I was trying to say, thus the assumption that once we move to solar, our CO2 problem would be fixed in is not true. CCUS has to deliver. So CCUS has to deliver in short to medium term. This could be a long-term solution when all green energy is available for you to purify your silicon, purify your germanium, and purify all kind of metals which are hardly at 1% concentration when you are trying to basically purify it. So coming back, let's look into, I think I am having 5 more minutes, Hansen? 10 more minutes. 10 minutes, okay. So if you see what I was trying to tell, that the bigger problem right now is that when you are going to capture CO2, you will have to rely on a material. Most of the material, either you're right now we have only one material for CO2 capture, that is MEA, TEA, DEA, whatever you call it. No other material has been, you would not believe, today there is no other material which is able to do CO2 capture. Huge amount of research is going on, but if you go and talk to most of these researchers, they will say, I can give you 2 gram, I can give you 5 gram, I can give you 10 gram. We need tons. There is no such material which can be produced in tons without producing any CO2. So today, I am going to give you in next 5 to 6 minutes a material which can be used, which you don't need to basically produce, and this is water. Water is available in plenty, and I'm not talking about fresh water, non-saline water, saline water, wastewater, effluent water, any water you want, you can use, and you can basically convert it into hydrates. And this is what I'm going to tell you. What are hydrates? Hydrates are hydrogen bonded water molecule, which basically encase a guest molecule which could be a gas, and it could be carbon dioxide. Okay, so if you have a gas mixture, let me go to this slide first. If you have a gas mixture of CO2 and hydrogen or CO2 and nitrogen, you have to just bring this gas mixture in presence of water and mix it. You will form a solid hydrate, and in the solid hydrate, the CO2 will be there, and in the gaseous phase, hydrogen or nitrogen, whatever you have along with CO2 will be there. So basically, a mixture which was of CO2 and hydrogen gases, now you have converted into a solid and a gas. Solid is primarily having CO2, and a gas which is mostly having hydrogen or nitrogen, which you can basically separate out. And since this is not a chemical reaction, this is a physical reaction, once you release the gas, this hydrate will dissociate and you will get your CO2 out of it. So what basically goes here? So hydrates actually form at certain temperature and pressure condition. As I was telling you, this is not a chemical reaction, it's just water and gas which comes together, forms a crystal. You are at right temperature and pressure conditions, this crystal will exist. And if you are away from this temperature and pressure condition, this crystal will not exist. So this is the phase diagram. It means below this, if you are at lower pressure, crystals will not exist. If you are above this pressure, it means you are at 10 degrees and you are at around 40 bar, this crystal will exist. So when you have a gas mixture of CO2 and nitrogen, and if you are forming hydrate somewhere here, because nitrogen forms hydrate over here, that is at 400 bar, you will form hydrate without any problem, and then you will be able to basically separate these gases. In terms of storage capacity, this storage of CO2 in hydrates are as good as chemical processes. And in terms of cost, hydrate process is actually not as expensive as amine if you talk about capture as well as regeneration cost. Because any chemical process will be cheaper when you are going to capture it, but then it will be expensive when you are going to regenerate that material, because you have to go to a higher temperature to regenerate that particular material. A physical process will be costly during the capture step because you have to go to a lower temperature or higher pressure to capture it. But then when you are going to regenerate, it will not cost you any money because it will automatically get dissociated when you are at certain temperature and pressure condition. So if you add both these costs, it will come out to be cheaper. However, hydrate process works better when you have more than 20% of CO2. If you have less than 20% of CO2 in a gas mixture, it's better to go for a chemical process. Now the question is, when we talk about a crystallization process, it's always slow. You have to worry about nucleation and growth of the crystals. Okay, so this is where we have done significant amount of work in last 10 years. We have looked into how to enhance the rate of nucleation and growth of hydrate. So if you see here, this particular slide, you saw it took 1200 seconds, but if you see in this particular slide, you will see these hydrates are going to form within fraction of a minute. And entire water will get converted into hydrate, which is basically, it's an unstirred reactor. So we have basically developed a process where we say that this is a reactor which is multi-bed reactor. You can feed in a gas mixture, CO2, nitrogen goes in from here. In these beds, there is nothing other than water. Okay? And then this gas, from this gas mixture of CO2, nitrogen, CO2 will come and form hydrate, which will be solid, and all the nitrogen will not go, and ultimately from here you will get pure nitrogen out of it. What you are doing here, you are not using anything else other than water. So no material generation, no CO2 generation. Because of this advantage, you see this is how the hydrates looks like when it grows. And these are just CO2 will be there, nothing else. So now we have captured the CO2. What you are going to do after that? I am not going to talk about utilization today, but what you can certainly do is that you can sequester the CO2. I will show you this phase diagram over here. This is basically seabed. This is the water height, and this is below the seabed. You see this is geothermal gradient, and this one is hydrothermal gradient. Okay? This is the phase diagram of CO2 hydrate. This is where hydrates will exist, and this is where hydrates will exist. But we don't want to target this region, because if someone tells you that we will pump CO2 in seabed, people will not agree. They will say, no, it will acidify sea, and all those challenges will be there. But this is below the seabed. What I am saying, 100 meters to 300 below the seabed, 70% of Earth is covered with sea. 100 meters to 300 below the seabed, you have unconsolidated sediments, which has huge amount of pores. Minimum porosity is 20%. It could be beyond that. You have almost infinite source of CO2 over there. What you have to do, you have to just expose those locations to CO2. Put in the CO2 there. The right temperature exists for hydrate to form. Because of the hydrostatic head, there is right pressure for hydrate to form. CO2 is there. In these pores, water is there. You have the right temperature and right pressure, and it will eventually get converted into hydrate. And it will look like this, which is, the photo is from Victoria Island beside Vancouver. This is methane hydrate. Under the seabed, millions of tons of methane hydrate exist for millions of years. These are methane hydrate which has been stable for millions of years. The amount of methane in these hydrates are twice as much as amount of methane and oil put together. So huge amount of methane already exists, and it has not dissociated from millions of years. CO2 hydrate has a better thermodynamics property compared to methane hydrate. So if you can put it under the seabed, you will be able to basically keep it stable. We have done the study. So this is the pilot plant which we have. We have done this study, and we have seen that CO2 hydrate will remain stable even if the seabed temperature rises by 12 degrees centigrade. What you have to do, you have to basically do something very similar than shale exploitation. In shale exploitation, you do the fracking to produce oil and gas out of it. Here you do a very mild fracking. Since it is unconsolidated sediment, you don't need to do that kind of a fracking. It will be very mild fracking which can be done by CO2 itself. And these CO2 will get converted into solid hydrate and will remain there for millions of years in solid form. This is how you will sequester the CO2. And we have done the data analysis. There is around 300 to 600 gigaton of capacity. There are other ways of sequestering CO2. LCA suggests that the best case scenario is to convert CO2 into plastics, which will lock it permanently. So this is, if you don't want to do geological sequestration, this comes more of a utilization of CO2 where it also gets sequestered. So polymerization of CO2 is one way. Manalik petrochemicals are actually already looking into this. And the other option is to basically sequester CO2 in concrete. See, some of these are distributed, problem of distribution. So if you are not having one large scale sequestration site, the investment is going to be significantly large. So this Carbon Cure in Canada they have done around 550 units of such CO2 sequestration site where they have basically pumped the CO2 in concrete formations, and so far they have sequestered 150,000 tons of CO2. The problem is this, 150,000 tons of CO2 is worth 2 minutes of CO2 emission. So that's all from me.